So we're going to be reviewing intermolecular forces and then also doing some problems to practice and make sure that we understand everything about intermolecular forces. So there are 4 different types of intermolecular forces, and I have them listed here in the beginning of the page. The first one is dispersion, which is also known as London forces. Every different type of compound will have dispersion forces. Dispersion or London forces is a type of interaction that you have due to the fluctuation of electrons. Since everything contains electrons, then everything will have dispersion or London forces. So your electrons, they're moving around all the time, and electrons are negative charges. So when two particles, they come close to each other, if the electrons are pointing towards the same direction, they will repel each other because they have both of them are negatively charged. So they will repel and they will move away. The region in your particle with a large negative charge will have a negative part, and meanwhile the other side will be positive, slightly positive. These are not charges like losing or gaining electrons. It's just a partial charge that will form because of the movement of electron or displacement of electrons. So there's attraction between opposite charges in your different particles. Remember, these are intermolecular forces, which means that these attractions are going to happen between different particles. It's not within the same compound, but it's between different particles of a compound. So everything has dispersion forces. The second one is dipole-dipole. Now here, for a substance to have dipole-dipole, that type of intermolecular force, you need to have polar molecules. Now you have polar molecules. For you to have a polar molecule, and this is a simplification, okay? For you to have a polar molecule, you need to have polar bonds. So for us, we're looking at polar bonds, not a polar molecule per se. So you have polar bonds, and I have the list of polar bonds here. A polar bond, it's a covalent bond that has a significant difference in electronegativity. You're forming a chemical bond between two atoms. Now one of them is going to have a large value of electronegativity, and this large and small are relative. It's large in comparison to the electronegative value that you have for the other atom in that chemical bond. Now that difference in electronegativity, what's going to cause is that the most electronegative atom is going to pull the electrons towards itself. That's the definition for electronegativity. Something with a large value of electronegativity, it's usually a small atom that can pull electrons towards itself very strongly. So when you have types of bonds like the ones that you have listed here, hydrogen with nitrogen, hydrogen with oxygen, hydrogen with fluorine, hydrogen with chlorine, the difference in electronegativity between these atoms in your chemical bonds, it's large enough for you to have displacement of the electrons. So the electrons in those chemical bonds, they are not shared equally. You can think about this as your two electrons, they're not right in the middle of that chemical bond. They will be closer to the most electronegative atom in the chemical bond, which is going to cause again a charge separation. So I'm going to do this with just one of them. The most electronegative atom between H and N is going to be the nitrogen, which means that the two electrons that you have share between the hydrogen and the nitrogen atom, they're going to be closer to nitrogen. What that means is that nitrogen is going to have a partial charge that is negative because your negative electrons are closer to that side of your bond. If the negative charge is moving towards the nitrogen atom, you're going to have a partial positive charge in the hydrogen. That delta, that's a symbol delta, plus delta minus. It's a charge separation, it's a partial charge, it's a permanent dipole. As long as that chemical bond exists, you will have your permanent dipole present. For all of your polar bonds, not just the ones with hydrogen, the ones with carbon also, for all of them, the most electronegative atom in those chemical bonds will always have a delta minus. The least electronegative atom in the chemical bond will always have a delta plus. Now, your dipole-dipole interaction will happen when your delta plus and delta minus in one polar bond are attracted to delta plus and delta minus in a different polar bond, in another polar bond in a different molecule, not between the same molecule, but between different molecules in your container. Third type of intermolecular force is hydrogen bonding. Now, hydrogen bonding is a special type of dipole-dipole. We can look at the hydrogen bonding as being the strongest out of the dipole-dipole bonds that you have. So my list of polar bonds that you have up here in number 2, it's a simplified one for number 3. Your dipole-dipoles, the ones that you're getting between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine, specifically those 3, they're also classified as hydrogen bond. So if you have a molecule containing these three polar bonds here, they have dipole-dipole, but also hydrogen bonding. And it's a similar type of interaction. You have the charge separation, giving you the delta plus and the delta minus for these 3 polar bonds here, and you will have attraction between opposite charges too. But since those 3 are the most polar bonds that you have in your list, these attractions are going to be stronger than the ones that you have listed for the dipole-dipoles, the other polar bonds besides these 3 listed here. Now, number 4, it's an ion-dipole interaction, and you have this type of interaction when you have a polar molecule and for us a polar bond. Okay? When you have something with polar bonds and you dissolve an ionic compound in that substance with polar bonds, your ions are going to separate in solution to give you positive and negative ions. If you have polar bonds to attract those ions, your polar bonds, you have your delta plus and delta minuses. So opposite charges will be attracting each other. So for ion dipole, we have a mixture. You will always have an ionic compound or a compound that will give you ions in solution mixed with something that contains polar bonds. And I will show you examples for each one of them. So another thing that is important from this list is the strength of your intermolecular forces. They are listed increasing strength. So the weakest one are dispersion or London forces. the strongest one out of the four is going to be ion-dipole interactions. So we need to know like the basic definitions for your types of IMFs, and also how to identify which ones you have in specific compounds. So I have a table here, and I'm just making check marks in the ones that are possible for each substance that we have listed here. So the first thing is that dispersion or London forces, that it's present in every single compound, which means that for dispersion here in this table, you have neon, oxygen, you have methanol, ethane, and then the last one here, and then so this is your substance, this is dispersion, which is the weakest out of the four. So all of these substances here, all of them are going to have dispersion forces. In all of them you have electrons. As long as you have electrons, you're going to have dispersion forces. So we have identified like dispersion forces for all four substances that we have listed here. Now for dipole-dipole, remember, for you to have dipole-dipole, you need to have one of your polar bonds present, at least one of them. If you check the first substance listed there, that's neon. Your element neon is not bonded to anything else. So you have a container with only neon present. The only type of attraction that you're going to have between your neon atoms in the container, it's dispersion forces, the one that is due to the movement of electrons. So we don't have dipole-dipole or hydrogen bonds, right? Because you don't have any polar bonds. Neon is not listed anywhere in your list for polar bonds, right? So that it's only dispersion. We move to the second one here, where you have oxygen, the element oxygen, your diatomic molecule. Again, if you check your list, oxygen here, it's a bond between two oxygen atoms. Two oxygen atoms, it's the same type of atom. So you have the same electronegativity value for both of them. The difference in electronegativity is not going to give you a polar bond because you have the same value for electronegativity, which means that the difference in electronegativity is going to be 0. That's not a polar bond, that is a non-polar covalent bond right there. So you don't have any polar bonds in your oxygen molecule, so you don't have dipole-dipole. If you don't have dipole-dipole, you're not going to have hydrogen bonds. You can have dipole-dipole without hydrogen bonds, but you cannot have hydrogen bonds without dipole-dipole. So moving to the third one, where you have methanol. Now, in this one, we know that we have dispersion. If you check your methanol molecule, that part right there, OH, it's a bond between hydrogen and oxygen. A bond between hydrogen and oxygen, it's a polar bond, which means that you do have dipole-dipole for that one. A bond between oxygen and hydrogen is listed right here as a bond that is going to give you hydrogen bonds. So besides having dipole-dipole in methanol, you also have hydrogen bonds. Now moving to the fourth one, where you have ethane. The ethane, you should have dispersion forces for that one. Ethane, you have a bond between carbon and hydrogens. Carbon hydrogen is not listed anywhere here as a polar bond, no. And you also have a bond between carbon and carbon. Also, it's not a polar bond. You don't have carbon-carbon listed here, which means that for ethane, since you don't have any polar bonds in that molecule, you're not going to have dipole-dipole, and you're not going to have hydrogen bonds. Now, for the last one here, we have trichloromethane. And for this one, you have bonds between carbon and Cl, carbon and hydrogen. Carbon-hydrogen is not a polar bond, so carbon-hydrogen is not going to give you dipole-dipole or hydrogen bonds. Carbon with Cl, this is going to look something like that. Carbon with Cl, it's right here. It is listed as a polar bond. You have a significant difference in electronegativity that will cause your charge separation in that chemical bond, giving you the delta plus and delta minus, not just one, but for all three of them. Since you do have polar bonds, you're going to have dipole-dipole for that one. Now, about the hydrogen bonds, CCl is not a polar bond that is going to give you hydrogen bonding. For you to have a polar bond that gives you hydrogen bonding, you need to have hydrogen bonded to nitrogen, oxygen, and fluorine. One of them, at least one of them. So you don't have hydrogen bonding for this trichloromethane. You do have dipole-dipole, but not hydrogen bonding. Now, how your intermolecular forces are going to affect physical properties in your substances. Physical properties that we're looking at: boiling point, melting point, and vapor pressure. Now, the higher the strength of your intermolecular forces, the higher the boiling point. It means that your molecules, they are attracted to each other very strongly. If you have strong IMFs, then to break those attractions, you will need more energy. That's why the boiling point is higher. The higher the strength of your intermolecular forces, the higher the melting point. Strong intermolecular forces again means that your particles are very strongly attracted to each other. So to break those attractions apart, you will require more energy. That's why you have a higher melting point. Now the last one is vapor pressure. Now vapor pressure, you have a liquid in a closed container. Okay. Think about that container as being half filled with the liquid. So you have your liquid in this closed container, and on top of your liquid, what you have is air. Okay? You don't have all the container filled with the liquid all the way to the top. You do have some space, so you have air right there. Now, when the liquid starts evaporating inside of that container, on top of your liquid, you're going to have the vapor of that liquid. The particles in that vapor, they're going to be moving around all the time, hitting the walls of your container, hitting the surface of your liquid as they move around. The more particles you have in that vapor phase, the higher the pressure. The pressure is due to the number of collisions that you have. As your gas particles are moving around, they're colliding, so the more collisions you have, the higher the pressure. Now, if you have strong intermolecular forces in your liquid part, it means that your liquid particles, they're strongly attracted to each other. If they're strongly attracted to each other a small amount of that liquid will evaporate to move to the vapor part that you have in your container. The smaller the amount of liquid that evaporates, the less collisions, the lower the pressure. That's why when you have strong intermolecular forces, the vapor pressure is going to be low. Strong intermolecular forces in your liquid part, your particles, they're strongly attracted to each other, which is going to cause a small part of your liquid to evaporate. The less liquid that evaporates, the lower the number of gas particles, then the lower the pressure. Now let's look at the first table here. For this one, we're looking at boiling points. We have listed three substances: ethane, formaldehyde, and ethanol. We are given the molar masses just to compare them. They have very similar molar masses. And now we're going to be looking at which type of intermolecular forces you have for each one. Ethane we already did. It was in the previous table. So for ethane, we do have dispersion. Actually, we can write down dispersion for all of them, because you have dispersion or London forces in every single compound. So I have dispersion for all of them. We already know that for ethane, that's the only type of IMF that we have, because you don't have any polar bonds. So you cannot have dipole-dipole and you cannot have hydrogen bonding for that one. Formaldehyde, you have a bond between carbon and oxygen. Carbon, oxygen, it is a polar bond. You can check that in your notes. It is a polar bond, which means that besides having dispersion, you're going to have also dipole-dipole. Now, in the last one, where I have methanol, you already did methanol in the previous table too. For methanol, you have dispersion forces. You have a bond between oxygen and hydrogen. That bond right there, it's a polar bond, which means that you have dipole-dipole. That dipole-dipole between oxygen and hydrogen, that right there, it's a polar bond, that it's also a hydrogen bond, because it's oxygen bonded to hydrogen. So besides having dispersion dipole-dipole, for that one you also have hydrogen bond. Now the boiling point part, this BP here means boiling point. You don't need to know these numbers by memory. This is just to show you the actual value, so you get to see what we're trying to go over. We have three different compounds with very similar molar mass. They have different intermolecular forces. We have ethane with just dispersion, we have formaldehyde with dispersion and dipole-dipole, and then we have methanol with dispersion, dipole-dipole, and hydrogen bond. Now, which one is going to have, or which one do you expect to have the highest boiling point? Your intermolecular forces, you have them given in increasing strength. The weakest one will be dispersion. From your list, ion dipole will be the strongest one. Well, we don't have any substance here with ion dipole, because for that one we need a mixture, and we're looking here at pure substances. We have all three of them are compounds. So dispersion, the weakest one, then we have dipole-dipole, and then we have hydrogen bonds. Ethane is the compound here out of the three with the weakest intermolecular forces. It's only dispersion. Methanol out of the three is the compound with the strongest intermolecular forces, because for that one you have dispersion, dipole-dipole, and also hydrogen bonds. If you check your note here at the top of the page, the larger the strength or the stronger the intermolecular forces, the higher the boiling point. So you should expect for methanol here to have the highest boiling point, because out of the three compounds, that's the one with the strongest intermolecular forces. For that one, we go all the way to hydrogen bonds. Now, I'm going to give you the numbers so you can actually see with the number. The number, you can find them online or in a book. You don't need to know these numbers. And these temperatures are given in Celsius. That's a negative 89, negative 19, something close to 65. Now, what that number is telling you, look, boiling point of a negative number for a boiling point, what that means is that that compound is actually a gas. For you to have that compound as a liquid, the temperature needs to be below negative 89. As soon as that temperature increases from negative 89 to any other number larger than that one, you will have a gas. So those boiling points as negative means that at room temperature, about 20 Celsius degrees, those substances are not even liquids. The intermolecular forces that you have between those particles are not even strong enough to hold your particles close to each other to give you a liquid state. Now for methanol, that's the only one with a positive temperature. It means that at room temperature, methanol is actually a liquid. Remember, for gases, we are assuming that there are no attractions between your gas particles, which means that you don't have any intermolecular forces between gas particles. In liquids, we start having intermolecular forces. That's why they are liquids, because you have attraction between your liquid particles. Now, the stronger the attractions between your liquid particles, the higher the boiling point. The boiling point is telling you that temperature at which your liquid is going to start evaporating to give you a gas, which means that the heat that is being added to a liquid to evaporate the liquid, it's actually being used to break your intermolecular forces apart. The larger the strength of your intermolecular forces, the more heat it will be required to break all of those intermolecular forces to evaporate the liquid. So the difference in your boiling points here is not due to the molar masses, it's not due to the type of compound that you have. That boiling point is due to the type of intermolecular forces that you have in your compounds. For methanol, the strongest one, it's hydrogen bonds. So you should expect to have a higher boiling point for that compound with strong intermolecular forces. Now in the second table, the bottom part of this page, we're looking at vapor pressure. So let's review vapor pressure. Relationship between intermolecular forces and vapor pressure, it's inversely proportional. The stronger the intermolecular forces, the lower the vapor pressure. So we have again ethane and formaldehyde. So we already checked the type of intermolecular forces for both of them. For ethane, we have only dispersion, and then for formaldehyde, we have dispersion and dipole-dipole. No hydrogen bond for this one. So the highest vapor pressure, you have stronger intermolecular forces in formaldehyde because you have dipole-dipole for that one. So you're looking for, if you want a high value for vapor pressure, a liquid that is going to have a high value for vapor pressure, it's a liquid that have weak intermolecular forces. The weaker the intermolecular forces, the more of your liquid that will evaporate to move to that vapor phase, the higher the vapor pressure. So out of these two, formaldehyde with dipole-dipole will have a lower vapor pressure than you will have for ethane here with weaker intermolecular forces. Since you're looking for the highest vapor pressure, you're trying to find out the compound out of your table with the lower interactions for IMFs or the weaker IMFs. If you're looking for a compound with the lowest vapor pressure, you will be looking for the compound with the strongest IMFs because the relationship between those two is inversely proportional. Now in this table here, we're looking again for the highest boiling point just based on intermolecular forces. If you check the compounds that you have listed here, ethane we already did. Butane and hexane. If you check your compounds, they look similar. You have carbon and hydrogen for all three of them. No other type of atom, it's just carbon and hydrogen. Between carbon and hydrogen, you don't have polar bonds. Okay? Carbon-hydrogen is a non-polar bond. The difference in electronegativity is not large enough for you to have charge separation in that chemical bond, okay? Or for you to have a polar bond. So for all three of them, carbon-hydrogen bonds, carbon-carbon bonds, it's only dispersion forces. So only dispersion. When you have different types of intermolecular forces, you can find out highest, lowest boiling points because the stronger the IMF, the higher the boiling point, which means that the weaker the IMF, the lower the boiling point, right? Is directly proportional. If one is increasing, so does the other one. But in here, all of your intermolecular forces are the same. You don't have dipole-dipole, you don't have hydrogen bonds, you only have dispersion. So to find out which one has the highest boiling point, only when all of your intermolecular forces are only dispersion, right? If you have different types like dipole-dipole, hydrogen bonds, ion-dipole, then you look at the strength of each specific type of intermolecular force. But in here, you're comparing substances with only dispersion. When you're comparing substances with only dispersion, you can actually look at the molar masses here. The larger your compound, the larger the molar mass, the higher the intermolecular forces that you will have as dispersion for that specific compound. The strength of your dispersion forces increases as the size of your molecule increases. Remember, your electrons are moving around all the time. The larger the compound means that the more space you will have for your electrons to fluctuate around in your molecule. So you will have stronger intermolecular forces for this dispersion type, specifically dispersion. So this problem looks very similar to the first one that we did looking at the boiling point. The difference between this problem and the previous one where you were looking for the boiling point too is that for that one you had different types of intermolecular forces and we were determining the highest boiling point based on the strongest intermolecular force present in your compounds. In this one you do have exactly the same type of IMF, which is dispersion. So when you have only dispersion, you can base your answer on the size of your molecule. Out of the three that I have listed here, hexane is the largest one. You have 6 carbons there compared to butane with 4 and ethane with 2. So hexane is the largest one, which means that you will have the largest molar mass, which means that you will have stronger dispersion forces for hexane than what you will get for butane and ethane. And what that means is that since hexane is the largest one, that one will be the one with the highest boiling point out of the three. So I have numbers here. You have this one already in the previous table for ethane, a negative number for butane, a negative number, and then for hexane we have 68. So you can actually see now, okay, my prediction based on the intermolecular force dispersion is hexane as the highest boiling point because it's the largest out of the three. Since I'm comparing only dispersion forces, the largest out of the three will have the highest boiling point. And now you can actually look at the numbers. You can search the numbers. You don't need to know these numbers by memory. And you can actually see that what you predicted based in intermolecular forces, it's true. We have negative number for the first two, which means that at room temperature they're gases. And then the only one that is actually a liquid at room temperature is hexane. And it will be a liquid all the way until the temperature reaches about 78 Celsius degrees. Now let's go over specific examples on how your intermolecular forces work. So I'm going to do a drawing, your NH3 and your H2O, like a Lewis symbol for both of them. Just one of each one NH3 and one H2O. Now I'm going to identify my polar bonds with the negative on the most electronegative atom. So between N and H nitrogen, so I have my partial charges. The negative one for the nitrogen because it's the one that is more electronegative in the chemical bond. And then the positive one for the hydrogen, which means that all of your hydrogens are going to have a delta plus. Now in the water molecule, the oxygen is the one with the highest value of electronegativity, and the hydrogens will be your delta pluses. So it's always the negative for the most electronegative atom and the positive in the least electronegative ones. Now you can see how you have your molecules with your polar bonds because you have that charge separation. The electrons in that chemical bond are going to be closer to the nitrogen than to the hydrogen. That's why you have a delta negative on the nitrogen because your electrons are negative and they're closer to the nitrogen. In the water molecule, something similar is happening. In your chemical bond between oxygen and hydrogen, your electrons are closer to the oxygen atom because that's the one with the higher value for electronegativity. Now, your interaction, your hydrogen bond, it's an intermolecular force, which means that it's happening between different particles. You have a positive, delta positive in that hydrogen for NH3. you have a delta negative in the oxygen in your water molecule. That line right there represents a hydrogen bond. It's a hydrogen bond connecting two different molecules, one for NH3, one for H2O. Now, this is a representation, just one possible hydrogen bond between NH3 and water. If you have a container of ammonia dissolved in water, you will have a lot of hydrogen bonds forming, not just between NH3 and H2O, but you can have hydrogen bonds between two different NH3, two different water molecules. If I add another water molecule here, you see, it's not that it's two different compounds or two different molecules. It's that you have two particles. They can be equal to each other. You can have two water molecules. The positive hydrogen in one will feel attraction for the negative hydrogen in another one. And that also represents a hydrogen bond right there. It's a hydrogen bond between two water molecules, and it's perfectly fine. As long as you have the attraction between your opposite deltas, you will have a hydrogen bond, because your bond right there, it's oxygen with hydrogen. You can have hydrogen bonds between your NH3 molecule. That's the negative right there. So the positive hydrogen in one NH3 can be attracted to the negative nitrogen in another NH3, and that's perfectly fine. That's also a hydrogen bond right there. The problem is asking you for the one between NH3 and water, so that one will be something like that one right there. The other one is just showing you that it's not just possible between two different compounds, but it's also possible between the same type of molecule. You had in your tables methanol, and you listed dispersion dipole-dipole hydrogen bonds for methanol. What that means is that your methanol molecule, you have only that one in a container, your pure substance, so the intermolecular forces are holding together your methanol molecules. It's not a mixture, you just have methanol in there. So all of your methanol molecules, they're going to be attracted to each other by dispersion, dipole-dipole, and hydrogen bond. Hydrogen bond between methanol and dimethyl ether. So something similar, I'm going to write down that one. That one. I'm not writing down all of them, okay? You don't have to. Just some of them to show a possible hydrogen bond. That's your methanol, the first one, CH3OH, negative on the oxygen atom, positive on the hydrogen that is bonded to that oxygen. In your dimethyl ether down here, you have an oxygen bonded to two carbons. The oxygen will have the negative sign. This is correct, because we're looking at the polar bonds, and that one will be between the carbon and the oxygen. Okay? Carbon, oxygen, polar bonds. Oxygen, hydrogen, polar bond, not CH. That's why I erased that charge that I placed in that hydrogen. So a possible hydrogen bond between your methanol and your Dimethyl ether, I have a negative here in the oxygen, a positive right there. That's an option right there. Again, you can have another methanol molecule feeling attractions or doing hydrogen bonds between two methanol molecules. You can have hydrogen bonds between two dimethyl ether molecules. That's perfectly fine. Now, the last one, it's an example of your ion-dipole interaction, which we didn't look at in any of the previous examples. For you to have ion-dipole, you need to have an ionic compound. I have lithium chloride, and you need to have something with polar bonds, which is this methanol molecule right there. So I'm going to write down again my methanol. Delta minus delta plus. Now your ionic compound lithium chloride, lithium group 1 plus 1, chloride group 7 minus 1. So when your lithium chloride dissolves in water, you get your ions, right? They separate because they're dissolving. If your ionic compound is not soluble in the solvent that you're using, in this case methanol, then your ions will remain together. They won't dissolve, which means that you will have the solid present. Lithium chloride is soluble in methanol because you have ion-dipole interaction. Ion-dipole means that your positive ion is going to be attracted to any negative delta minus in your compound. So my methanol molecule here has a polar bond between oxygen and hydrogen. That oxygen has a delta minus because it's the most electronegative one. So you have that attraction. Negative ion will be attracted to the positive charge in your polar bond. So if that attraction between your polar bond and the ions in your ionic compound is strong enough, your ionic bond will break apart and your ionic compound will dissolve in that specific substance. If you have an ionic compound and you're trying to mix that ionic compound in a substance that has no dipole-dipole, you don't have that attraction between opposite charges, which means that it's very likely that your ionic compound is not going to dissolve in something without polar bonds.